that is that. All right, cool. So again, last time we were looking at linear things, everything degree 1. We were looking at actual lines or space lines. The general term for them is space curves, but there are right parametric equations for lines. We had symmetric equations for lines, and then we looked at planes, the component equations and the vector equations for planes. So today what we're going to do is move from the linear up to the degree 2. So akin to, back in college algebra, moving from linear functions up to quadratics or parabolas, we're going to move to the general form of degree 2 equations in 3D. So these things take on the shape of essentially the 3D version of conic sections from pre-calc, right? And what were the conic sections? They were the shapes we'd get if you had a cone and you sent a plane through it at a cross section, the corresponding curve that you would get, right? So the nice easy ones were when you if you got a cone like this, right, and you sent a plane through it. I guess I have a graph in front of me. I could just draw it out, right, instead of using my hands, but I guess I'm a talk with your hands kind of guy. So if I have a cone and I sent a sheet of paper through it, right, what would be the intersection there but a circle, right? And all the different permutations of doing this. So if I instead sent the sheet of paper, straight down, what would happen? I'd get some sort of parabola looking thing, right? And all different sorts of variations of that. If you sent it at a slant angle, you'd get an ellipse instead of a circle, right? So all the different degree 2 shapes that we'll see now in 3D, that's what we're going to be looking at. First, though, I want to talk to you about traces and cylinders, because that's going to be kind of the starting point and a bit of the orientation ideas in order to look at these 3D shapes and not get totally lost. All right. So let's jump into first what I mean by a trace, and then we'll just look at some examples. So traces are really like cross sections of graphs where we essentially, like the mechanics of it are to hold a variable constant hold one variable constant and visualize the 2D curve associated with that equation. And I'll give you examples of how that works. And we've actually kind of done this in class already, or at least I've done it when lecturing, to say let's pin z to a certain fixed value and see how x and y vary, right? So to give you a quick example, and we'll play with this a little bit more, but if I have x squared plus y squared plus z squared equals 1, we know this is the unit sphere, right? And so what we would do is take maybe the z equals 2 trace and see how that looks. And so, well, actually, that's not going to work, is it? How would we have a z equals 2 trace if this thing has a radius of what? 1. Come on, Mally. Trick question. So if we had the z equals 0.5 trace, all right, what would happen? Well, it's like we pretend that z is a constant 0.5. So then x squared plus y squared plus 0.5 squared equals 1 gives us a resulting 2D curve that we can draw. This is going to be a quarter, and we subtract it to the other side, and you get what? X squared plus y squared equals 3/4. And so what does this look like? Well, in 3 space, it looks like a circle that's parallel to the xy plane, and it's at a z height of not 1, but at a half. And we've got this, right, circle of radius, radical 3/4. So this would be this trace. And what we can do is shift what this value is and get a sense, right? If we shifted it up closer to 1, we'd get a smaller circle. As we got closer and closer to the origin, we'd be approaching the unit circle. And so what's nice is by holding one variable constant and letting the others vary, we can get these 2D graphs that tell us what the 3D graph looks like without having to lumber through it, right? And often those are really tough to draw. And having it's like building a contour map. If you've seen, topographical maps, it's the same exact idea. Concentric rings, just seeing a few of them or a series of them on a 2D paper, your brain can draw in the extra dimension, right? You don't need to actually physically draw it. So it's a nice tool. So that's what we mean by traces, and we're going to play with that when we graph quadric surfaces. So we briefly discussed what a cylinder is. And does anybody remember how we kind of loosely or casually defined a cylinder?
Just like a circle in R2, except we still don't have Z.
Right. Yeah, last time we said it's an equation in R3 missing one variable. And so if you had a circle in R2, but now you bring it into R3 and you graph the same equation, you're letting Z vary freely. And so what happens is you're getting a circle kind of projected down an axis, right? Projected down the Z axis. So for example, if we had this guy, just x squared plus y squared equals 4. It's a circle of radius 2, but in R3, its Z coordinates can be anything. So it looks something like this. But really, we're going to shift that definition now to be that it has cross sections or traces that are made by this generating curve. So here the generating curve is this circle equation, and then we shoot it down an axis, and we project it down this axis. It's sometimes called the directrix, where it kind of stretches out that dimension, right? So every time you slice it, you're getting the same shape, rolling down an axis, and that's what we call a cylinder in 3D. Okay, so that differs from that solid geometry idea of a cylinder. It doesn't have to be a cylinder that's round. You could have a parabolic cylinder. So if you think of, let's say, z equals y squared. Okay, how should this thing look? Well, what we can do is look at traces. For example, here looking at the x equals 0 trace, when x equals 0, what does z equals y squared look like? Well, it looks like a parabola, right? Not y squared. Looks like a parabola in the zy plane, right? Where the height depends on squaring the y coordinates. So it looks something like this. And if we looked at, let's say, the x equals 1 trace, well, when x equals 1, still the curve is z equals y squared. That's the generating curve. It doesn't care what x really is. So if we came out here to where x equals 1, it would look something like this. It's not totally accurate, but x equals 10, same thing. Came down here, z equals y squared. We're getting a parabola. It shouldn't be this wonky. Maybe it's a little bit tighter down here. That would makes more sense perspective-wise. And so what we get is this kind of curtain-looking thing. Here's x equals 10. all those cross sections, wherever you slice it parallel to the ZY plane, you're going to get the same curve. All right, and so that's what we call a cylinder. The traces are all projected on top of each other like that. Okay. So I thought I had a fun example there. You say define fun, Mally. I know. Okay, here's one. It's not fun, but it's important to review. Some equations that we're going to need to remember are the ellipse and the hyperbola, which you probably haven't seen in a while. So here, let's look at one more. Consider x squared plus 4z squared equals 4. And visualize with traces. So another way you can do traces, I mean, I kind of drew this in 3D. I drew these cross sections. Another way you can do it is just pretend that you're in the XZ plane. And think about, if y equals 0, again, this is a cylinder, so it doesn't really respect y. Y can be anything. But we should draw out what this is going to look like in the XZ plane. And then we can shoot it down the y-axis, and we'll know what it looks like in 3D. So what does this thing look like in 2D? X squared plus 4z squared plus 4. Well, it's not quite a circle, right? This is actually an ellipse. And if you recall, a 2D ellipse has the equation x squared over a squared plus y squared over b squared equals 1. This is for when it's centered at the origin. A and B tell you how far to stretch out the axis of the ellipse. So here this is in the XZ plane, which is no problem. So we're just kind of pivoting to the side. And then, well, actually, we're flipping up, right, to the wall. And then to solve it to standard form, we're going to need to divide everything by 4, so we drive this to 1. That's the only way that this is in standard form. So we divide everything by 4. You get, what, x squared over 4 plus z squared equals 1. So what that tells me is this thing on the xz coordinate plane hits at plus and minus 2 on the x and plus and minus 1 for the z, and we get an ellipse like that. So we get an elliptical cylinder because since the y trace we choose, since y isn't in this equation, it's like this for y equals 0, it's like this for y equals 100, and y equals negative 1,000, right? And so on and so forth. So the trace is not super helpful here in terms of picturing any sort of change, but gives us a sense of what that cross section should be, and then we can stretch it down the axis that it's lying on. Now, when you're working on problems involving these things, whatever, for cylinders, whatever variable is missing, that's the axis that's being projected down, right? Because the plane that's perpendicular to that axis is what the function's going to be most likely defined in, right? So xz plane is perpendicular to the y-axis, so it's sending this thing down the y-axis. So again, this curve here in 2D that we shoot into a 3D cylinder is what we call the generating curve. So in 3D, let's just finish this off. In 3D, what does this thing look like? So xz plane is right here, so it came out to 2 in the x and 1 in the z. So something like this. So is the y equals 0 trace. If y equaled 10, would have gotten something out here like this. Everywhere you slice it, same thing, and we'd get, that was a terrible not to scale ellipse. Obviously, these things don't need to be perfect. Let me set the bar for that. But you can see anywhere you slice it, it's the same thing. Okay? So, this is going to generalize to other sorts of curves as well. If you recall the hyperbola, right? What was the hyperbola? Something of this form. And I can actually show you my graph here. So this guy, right, is the hyperbola when a and b are 1. And then if we switch the order around, right, it takes on the other direction. So whatever term is positive, that's the axis it's kind of lying on. All right. And then from there, you think about this as being what the z equals 0 trace in R3, because we're in what plane right now? The xy plane, right? So if we're in the xy plane is really the z equals 0 trace of all the curves you've ever seen in R3. And so that's the case here. And if we think of this as a cylinder, these are the slices going up. And so what you're going to get is like this set of curtains, essentially, bending inward like this, straight up and down. And this is looking from the top down on the z-axis, what the cross sections will always look like. So it's the hyperbola. And it looks like this, right? So I'm going over these as well because we're going to want, when we talk about all the different degree 2 equations that we can have in R3, we're going to have some combinations of these things that are going to pop up. So to remember the hyperbola, to remember the ellipse, remember the circle and the sphere, and the parabola. So what is it about a cylinder? When you send it down its axis, it doesn't change its cross sections or its traces. That differs from what we call a surface. Whereas a surface, its traces are going to change depending on where you are in space. So those are the kind of more interesting examples that we're going to jump into. So any questions so far on cylinders or creating traces? All right, it's not too bad. It can be tough for a lot of people to visualize this, so give yourself some time to kind of play with them. I'm going to provide a 3D graph link that you can go in and tinker with. And, I really encourage you to just actually play with it, right? Play with the parameters, see what changes, so you get that knowledge in your bones, right? Instead of just having to think it through every time. I'll tell you that I have not committed these graphs to memory. I kind of reason through the traces every time myself. So just by looking at the equation, I kind of reason out what is this thing. That's a helpful way to go. So let's look at now the more interesting graphs. Quadric surfaces. All right, so again, surface means the traces are going to change. You can think of just the surface of any object, right, in 3 space. It's not necessarily a cylinder. And what quadric means, it's a generalization for like quadratic. It means degree 2. So in general, it's all of the things that look like this, and this is going to look intense, but we're going to only really play with the nice, kind of perfect versions of this. But it really does extend to anything of the form ax squared plus by squared plus cz squared plus dxy plus fxz plus, nope, I screwed that up, eyz. Remember alphabetical order? That's a whole thing. Plus fxz plus gx plus hy plus iz. Oh, looks like they don't use I in the text. I would, but it might be a reserved letter, like the 13th floor in a hotel. Plus k equals 0. So again, this is general form, which means it's including every possibility, and a lot of those possibilities are when most of these coefficients are 0, right? So they're not all this intense. But we want to be inclusive of all possibilities. So the basic surfaces that this includes ellipsoids, paraboloids, elliptical cones, and hyperboloids. So again, think about these shapes in 3D. The cylinders are pretty easy, where we just let one variable range freely, and we kind of get a curtain that looks like a parabola, right, or a hyperbola, or a circular cylinder or an elliptical cylinder. But if we make the variables contingent upon each other, depend upon each other, in this general form of a quadric equation, then what's going to happen is you're going to get different kind of combinations or permutations of these things. So what does it look like when we kind of have something that has parabolic cross sections in one direction and elliptical cross sections in the other, right? Coming at it from this way, the traces look like parabolas. Coming at it from this way, they look like ellipses, right? Or that it looks like ellipses with different configuration, right? One's maybe longer this way than going this way. So these are the kind of different basic shapes that we're going to look at. So the first one up is ellipsoids. What I want to do is do the traces for one, then I'll show you the general form. Okay, so let me do that. Because I think thinking about them from the traces first instead of trying to memorize the forms for these things is a much better way to go. So let's say visualize through traces the equation x squared over 4 plus y squared over 9 plus z squared over 6, not z to the 6th. Okay. So what we can do is break it up by fixing one variable and looking at what happens to the others. So some pro tips here. One, choose one variable at a time. And two, choose nice values for traces. As reasonable as you can. So to start off, let's say I take z equals 0. So the z equals 0 trace is really in the xy plane, right? So when z equals 0, xy looks like this. So the curve is really x squared over 4 plus y squared over 9 equals 1, which is an ellipse. Intersect at 2 and negative 2 on the x. And I should make this a little bit longer here. Two and negative 2 on the x-axis, and 3 and negative 3 on the y. So it'll look something like this. And then what we can even do is on the same set of axes come up with the next trace. So z equals 0 is a nice one. Why is that nice? Because we just removed z from the equation and we got the resulting cross-section. So if I maybe made z plus or minus radical 6, what would be nice there is this would reduce to 1. It might be a little bit nicer to play with. So it might not always work out, but let it be, let's say, radical 6. So if z is radical 6, then we see that this thing becomes 6 over 6 and reduces to 1. And so we get x squared over 4 plus y squared over 9 plus 1 equals 1. And so when we subtract 1 from both sides, we get x squared over 4 plus y squared over 9 equals 0. So this isn't the nicest thing in the world. So what we can do is not use that value first off. Because what is this thing? Is that going to be too far out? Oh, it's right at the tip of it. So that means you're just going to get the singular point. So it's not a good one to choose here. Let's instead choose z equals 1 and just see how that goes. It's not great because you've got a fraction, but it's not the end of the world. So if z equals 1, then this becomes x squared over 4 plus y squared over 9 plus 1 over 6 equals 1. And so what you can do is solve for this piece, this x squared plus y squared piece on the left. X squared over 4 plus y squared over 9 equals 5/6. And then drive both sides to 1. Now this is why it's a little bit tougher, and you'd probably use a graphing utility or choose a nicer value, because it's a little algebraically intensive. So drive the right-hand side to 1 so that you get a standard ellipse equation. What do? I multiply both sides by 6/5, right? And I also want to say, too, that sometimes just getting one trace is sufficient in one direction. Sometimes not. So what we'll get is, 6x squared over 20 plus 6y squared over 45 equals 1. And then you can use a little trick here which is, right, if this is really 6 over 20 times x squared plus 6 over 45 times y squared equals 1, we can instead write this as, you're going to be like, Mally, what the heck are we doing here? You can instead write this like this. Because now I have my a and b, right? So if I wanted to trace it out, I've got a is the square root of 20 over 6, b is the square root of 45 over 6. Not super important, but a nice trick to have up your sleeve. So what does this look like? Well, square root of 20 over 6, let's just punch that in real quick. Just because I want to give you guys an idea. So this works out to be, so your a value is like 1.86, and your b value is like 2.7. So what does that mean? This is an ellipse with intercepts. Excuse me there. So this is an ellipse with intercepts on the x-axis of 1.8 and negative 1.8. So x equals plus and minus 1.86, and then y equals plus and minus 2.74. So back on the graph, right, it's a little bit higher. So when z equals 1, coming up to 2.74, negative 2.74, and then 1.86, negative 1.86. So we get another ellipse. But when z equals 1, it's a little bit higher and tighter circle, a tighter ellipse. This continues up and in the negative direction as well. If you continue this in the other planes, right? So again, you're kind of reading this like a contour map. Right? This green is the ground level. This yellow is one floor up, right? And as you increase z by 1, you'll see that this will continue happening, something like this. If you do this with y equals 0, then we're really looking in what plane? The xz plane, right? When y equals 0, what we're left with is this curve. And so in xz, this again comes out to 2 and negative 2, and it comes up to radical 6 and negative radical 6. Which is a little bit bigger than 2 and a little bit less than 3. If you don't have radical 6 memorized, shame on you. Just kidding. No one has that memorized. And then we draw in the trace here. Again, it's like the ground floor contour map. Not a circle. Something like this. And the same thing happens if I let, again, this is the xz plane, so this is the left-hand wall, right, of the first octant. That's what this looks like. And if I let y equals 1, I came out a little bit, that same thing, let me put this in yellow. If I did y equals 1, same thing would happen, as it would become a tighter ellipse. As I work my way out. Kind of becoming this mound, and the same thing happens in the opposite direction too. You can imagine similarly for x equals 0. Actually, I'd like you guys to just try this real quick. What would the x equals 0 trace look like algebraically and then also graphically. So again, you're going to get what ellipses in the YZ plane, plus and minus 3 for Y, plus and minus radical 6 for Z. So it's a somewhat squat ellipse. It's longer in the Y direction. Not really giving the computer a lot to work with here. Something like this. Again, these pictures don't have to be perfect, but as you see, as you move out your x equals 0 and x equals 1 would look something like this. X equals 2 would look something like this. Oftentimes when you're looking at graphs of traces, this is implied. We might label one of them, and then it's assumed that there's an equal spacing between the variables' increments. So you increment x up by 1 or 5 or whatever to see what the next trace would look like. So I have a program that's rather talented at drawing, unlike myself, and I will share that with you here. And so you can see here, let me first orient ourselves. I'll click this off. I'm actually going to turn off those. Okay, so you can see here's the XYZ. We're kind of boxed in. I'm going to spin it so that we really are just looking down into the YZ plane and graph this surface. And what do you see the cross sections are? They're ellipses, right, that are coming up and out. And your x equals 0 trace is exactly what we just did. It comes out to 3 and negative 3 on the y-axis and up to radical 6 and negative radical 6 in the z. And if we rotate ourselves to be looking into the xz plane, and we kind of are projecting down the y, or looking down the y, well, which one was that? That was our second one here, where we saw, yeah, this was the taller ellipse, right? Plus and minus radical 6, and on the x-axis it was plus and minus 2 for that trace. And then as we extended out in y in both directions, it got tighter and tighter. And then again, looking down on top, where it's just the xy plane here, you see the same ellipse. So this thing in 3D really has ellipses in as cross sections from any way you look at it in terms of the coordinate planes or parallel to the coordinate planes. So it kind of looks like a football or a blimp, right? And so those A and B values that we used determine where it's intersecting those axes. So it's determining the stretch of this thing in all these directions, right? So in general, what this looks like, x squared plus y squared plus c squared plus, x squared plus y squared plus z squared all over a, b, c squared equals 1. When all those a, b's, and c's are equal to 1, it is a sphere, right, like we've seen before. But if we move that a value up, it's going to stretch along the x-axis. Same with the b value. If I increase that, it'll stretch along the y-axis. Shrinking or increasing z stretches it along that axis. All right, and this is what we call an ellipsoid.
So if we slice it on one of the parallel to one of the axes, it makes an ellipse every time. And will it still make an ellipse if we slice it on an angle? Or will that be like distorted?
It would be distorted, yeah. Yep. So the purpose of traces is really, I mean, I can see there being some application of taking traces at a different orientation. But for our purposes, just visualizing these things, taking standard traces where you're holding one variable constant and looking at the others, looking at them parallel to these planes is the most helpful. But yeah, it's not if you slice it any way you'll get ellipses. All right. And actually, it might happen for an ellipse. It might happen for an ellipsoid if you think about slicing this. But for the other surfaces, that does not hold up. So that's really what I was more thinking of. So this is an ellipsoid, so I'm going to show you the standard form for that. And again, I'm going to put these, the visualization in the class notes so you have a chance to play with it. And obviously this is, maybe not obviously, this is centered at the origin. You would shift X, Y, Z by, H, J, K, if you had a different center, but we're not going to really play with that too much. We're just introducing these shapes. But you'll hopefully see its striking resemblance to a sphere, because a sphere is a special version of an ellipsoid, right? It's where A, B, C, and all are all 1. And all the terms are positive, all the terms are squared, they're on the same side of the equation. They're equal to 1 on the right-hand side. So that is ellipsoids, and the cross sections of traces are all ellipses. All right, so I want to take a look at another surface, unless there's questions on that. All right. So let's look at the following. So visualize z equals x squared over 4 plus y squared over 4 minus 6. It says degree 2 terms in x and y and z. Z is a single degree, right? What does this thing look like? Well, if we look at the Z traces, at Z equals 0, or in the xy plane, we've got 0 equals x squared over 4 plus y squared over 4 minus 6 equals 0. So if I just solve for something that looks a little bit more familiar, what I'll see is that, x squared plus y squared equals, 24? This is really a circle of radius radical 24, right? So in the xy plane, looking down at z equals 0, I just get a circle. What's the square root of 24? Just less than 5, right? So a circular cross section, and if I let z scale up, let's say I let it be, let's say I just let it be 1, then the same thing would happen. You'd solve and you'd get a circle, which was what? 28. Right, so it's radical 28 is the radius for the next trace up, so it's kind of getting bigger as we're moving out. Wait, is this opening downward? It has to be. Okay, good. So yeah, if you looked at like z equals -2, moved in the other direction, you'd get this -2 on this side. Again, it takes a little bit of work. You'd add this over, multiply, you'd get what? A circle is equal to 16, so that's a radius of 4. So if you go in the other direction, it's kind of tightening up as we get lower and lower. So already, what are you kind of thinking this thing's taking the shape of? If we look down on it, and it's got these concentric circles that are from inside. So here's z equals -2. Here's z equals 0. Here's z equals 1. -2. This contour map, this is like a bowl that's opening up, right? So these are the z traces. Let's just take a look at the x traces. So let's say if x equals 0, then this thing is what? Just y squared over 4 minus 6, which essentially is a what? It's a parabola that's been shifted down, right? This is really 1/4 y squared minus 6. So it's a parabola that's been, kind of bowed out a little bit. It's scaled down, so it's a little bit flatter, and then it's been shifted down by 6. So this thing in the x trace means we're in the yz plane. So z depends on y. It's parabola that's been shifted down. I'm just going to kind of sketch it. It looks something like this. Not like that. Goodness. And if I let x increase, All right, I came out a little bit. What's going to happen? This is all going to shift upward. And maybe I should use a nicer value for x now that I can. All right, maybe I'll use x equals 2. Because then z, this keeps glitching out on me, z equals 2 squared over 4 plus y squared over 4 minus 6. So that's z equals, this is 1 minus 5, so that's really 1/4 y squared minus 5. So it's just the same parabola, but shifted up. So when we look down the YZ plane, which is right the front wall of the room, they look like parabolas that are shifting up. And the same is true when we look at the XZ traces, right? The left wall. The parabolas that are moving up. So what we end up seeing is something that has circular cross sections top down and parabolic cross sections from side to side. And so this is what we call the elliptic paraboloid. Any way you slice it, looking down this direction, it circles all the way around. And if you slice it in the XZ or the YZ, then you're getting these, parabolas facing those directions. So it's cool. It's kind of like a bowl or a vase. Has a vertex, but infinitely opens in one direction. This can lie in any direction. So it can be in the Z direction, X direction, whatever it is. So that depends on the structure, and a lot of these are going to be that way. Okay, the ellipsoid was kind of a little bit simpler in that way, but now if the order of the terms is going to matter, and so we need to just be aware of how that shifts the graph. So in general, for a paraboloid that's upward facing in the Z direction, it looks like this. Z over C equals x squared over a squared plus y squared over b squared. And here we had this constant where it's just been shifted down by 6. So here this one was, if this was like my axes here, this has just been shifted down to z equals -6 here. So that constant's not present in the general formula, but if you have it there, that's what it means. Again, A, B, and C all doing some shifting along those axes. And again, the way I see these when I look at them, I hold each one constant and see what the resulting function would look like. So z is over here by itself. If I said, all right, this is no longer y squared, this is some k, well, then really what I have is a function z equals x squared plus a constant. What is that? Well, that's a parabola, right? So the cross sections in that direction are going to be parabolas. I do the same thing for x. I say, well, if x is constant, then z is y squared plus a constant. That's a parabola that's been shifted up, right? And then the other way around, hold z constant. I've got a function of x squared plus y squared equals something. Well, that's probably going to be a circle, maybe an ellipse, right? But definitely going to be something like that. And now I have an idea of what shape this thing is taking. Does that make sense? Okay. So break each one down, hold each one constant, think about what the resulting function would look like. You can memorize this table of the quadric equations, but I don't think that's worthwhile. Okay. So that's an elliptic paraboloid. Few more to cover here. Actually, I'm going to switch it up a little bit. I'd like you to take a look at this. You guys see that okay? It's not too small. Okay. Knowing what you know, try to match up the graphs you see with the equations. So I'll give you guys a couple minutes to think about this. And then I'll ask for, if we have any, if we've got them all figured out, if we got a couple, what we know are strong links and what might be question marks for us. Let's take a couple minutes, reason it out based on what we've done so far. Make it a little bit bigger here. right, so what are we thinking so far? Do we have any for sure? I know this one. Or this can't be this. You can just shout it out.
I think I've got 1 and 4.
One being four.
Oh no, 1 is 6.
Number one is graph 6.
I agree.
We agree?
3, yeah. 3 is number 2,
3 is number 2.
maybe.
All right, let's go back and just so for people who didn't see that 1 is 6. Why is 1 6, Nate?
Because it's an equation of what's that word I'm looking for? Hold on. Ellipsoid.
Ellipsoid. That's right. It's what? It's stretched in the z direction, right? X and Y, the cross sections are circles. So A and B are equal there, stretched in the z direction. Yeah, I agree. Okay, and every way, if you hold X constant, you get an ellipse. If you hold Y constant, you get an ellipse. If you hold Z constant, you get an ellipse for those cross sections of those traces, right? Awesome. So for number 3, you said?
I think it's number 2 because the X is there's no X in it, which means X can be anything, so it would be. And that's the only one that's like that. So I took a guess.
Okay, nice. Yeah, so go ahead.
I was going to say, by that same kind of logic, that it's missing X, number 4 should also
Yeah,
be
I
Roman
just
numeral
saw
4.
that.
Yeah, and somebody said that they agree with that too. Yep.
Yeah, but I thought number 4 was 4, right?
4 was 4.
Yeah, I agree with that.
4 is 4. Yeah, and let's unpack a little bit more Y as well. So for
So we have a hyperbola in the ZY cross section, and then our equation doesn't have an X, so we can just vary it freely in that direction.
right. And so you see with graph 4, the cross sections in the YZ are hyperbolas, right? And then if you look down the X is just being stretched in either direction, so that's fine. So yeah, that is a cylinder. It's a hyperbolic cylinder. And then for number 3, it's an elliptical cylinder, like we looked at in like the first example, right? Very similar. I think we had one in X and Y. So in the YZ traces, it's a cylinder, or it's the ellipse. Again, X is allowed to vary. Great.
So then I want to make number 6 Roman numeral 1, because out of the remaining options, it has an absolute value, and the remaining options the other 2 remaining options have essentially a positive and a negative.
Mm.
For Z, yeah, that's what I was thinking too.
So for 6, you're thinking it's number 1.
Yeah.
Okay, any other discussion there?
Well, I guess if you look at the values of it, it never goes above 0.
Yeah.
See, is it drawn like that?
Yeah. It's living in the negative values of Z.
Yeah, so probably scratch that, right? When we don't have too many negative absolute values.
Withdrawn. Redacted. But I see the point, right? We see maybe some resemblance to like a hemisphere there, but maybe not quite. Is there another one that fits the graph of 1 a little bit better?
Well, that would have to be 5, but that one.
2, I think. Number
I
2.
don't know.
Because number 2 says that after, like the equation of number 2 says we're going to make it negative after we take the square root.
Right.
So we would take the square root of our sphere, cut it in half, and then flip it upside down.
Right. Square both sides, right? Bring the x and y terms over, and what do you get? You get x squared plus y squared plus z squared equals 4, which is a sphere. But if you square root and take the negative root, then now we're talking about the hemisphere that lives in the negative z quadrants, right? Or octants. Good. So yeah, 2 is graph 1. For the others are a little bit weirder. Maybe we'll pause and come back to this.
I guess 3 looks like it's a little sharper. And if we have an absolute value in there, that tends to make a sharp V.
Mm.
And 5 looks like a little smoother. So maybe 6 is number 3 because it has a sharper angle to its coniness.
Meaning 6 is graph 3?
Yeah, possibly, yeah.
Okay. Seems to lend itself a little bit to that. Yeah, so let's pause there. We'll pivot to some notes, and then we'll come back to this. We don't have any other strong, compelling cases. And that's actually right. For 6 is graph 3. And the next surface we're going to look at is actually the cone, and we'll see why that's the case. All right. So let's pivot back here. Cones or elliptical cones. They have this general form. X squared over a squared plus y squared over b squared equals z squared over c squared. Another way you could see this would be it all solved for 0 where the z is negative, right, and the x and y are positive. And you can see how that last equation we were working with could be played with to produce something in this form, right? Square both sides. You've got the z squared on one side and your positive x squared and y squared on the other. So, why is it of this form? Well, if we think about the traces, if x is 0, then what I've really got, if I solve for z here, I get the lines z equals plus and minus c over b y, meaning there are two lines that intersect at 0 with opposite slopes. And then the same is true for when y is 0. If I solve for z, I square root both sides, I get z is a linear function of x plus and minus, right? So that means I got one going this way, one going this way, crossing through the origin, right? At x equals 0, at z equals 0. And that kind of sounds like what the cone is doing, right? It's crossing through that singular point. At z equals 0, it is the point 0, 0, 0. And if I let z equals k, so if I just let this equal some constant, what does this thing look like? Well, they look like ellipses, right? I can clear the k down to 1 and I'll get an ellipse general form on the left. And so as we slice out in the z direction positive and negative, I'm getting ellipses. All right, so they're kind of like this. Oh. And then at the coordinate planes, when x equals 0, zy is doing something like that. And then likewise for the other plane is a little bit tougher to draw with the perspective here. But that's essentially what we're working with. So again, just kind of chasing down the conclusions of just the way this equation is set up. Let z equal 0. What are you going to have? Two intersecting lines at that point. Let z equals k. What do you see? These ellipses as the cross sections. Okay, so it's an elliptical cone, has that form. And this is somewhat again, a place people get not confused, but a little bit muddled because words mean different things right now, right? You thought that the cone probably was just the singular point, but really the true kind of cone that we talk about is this cone that is reflected through on the other side of the origin. So it's got these two shapes, or these two big components to it. And that's why when you slice it with a plane, like for the hyperbola, you're getting the mirror image up and down, right? Because that you're slicing the actual, mirrored cone, the full cone, instead of just a half cone. So if you read or hear someone mention a half cone, they're really talking about what you used to think of as a full cone, right? So obviously people are going to get a little bit confused, but just to know, this is the real full cone here. Elliptical cone to be more general because the cross sections don't have to be circles. All right, and the last two shapes, last two quadric surfaces. Are the hyperboloids. They come in a few flavors. So actually, I won't even break it up like this. We're just gonna break it up one by one. We'll say that hyperboloid of one sheet. How many sheets? Just the one. Why just one? Well, what we mean by that is that this surface can be drawn using one single, sheet. If you were to, cut a piece of paper and wrap it into this form, because its sister curve, you actually need two sheets because it's split up in the middle. I'll show you that in a second. But a hyperboloid of one sheet, it has traces of hyperbolas, so that's in the name, and then ellipses in the other direction. So let's take a look at why. So, if you look at y equals 0, what are you getting? X squared minus x squared over a squared minus z squared over c squared equals 1. This is a hyperbola, right? In the xz plane. When x equals 0, you've got y squared minus z squared. So you've got hyperbolas in the yz plane. And then if I let z equal 0, I've got an ellipse, right? X squared over a squared plus y squared over b squared equals 1. So what this thing looks like I haven't drawn one of these in a little bit, is an ellipse in this direction. They kind of look like those nuclear power plants. Ellipses is cross sections in this direction, and in the other two directions, they have these hyperbolic curves. So think those, nuclear towers. So it's a hyperboloid of one sheet.
So is the one constricting like the smallest diameter inside, and then the like A's and B's constricting how it bends?
It's more that A's and B's are dictating that because you would just drive the right-hand side to 1 to get it into standard form. So it's really those parameters of A, B, and C are in the driver's seat of the shape of this thing, if that makes sense. It's up to them. So the 1 stays fixed, as long as it's in this form. And the A, B, and C are really what dictate the tightness of this ellipse. Right, so for at the z equals 0 trace, if that's the one you're talking about specifically, C and B are dictating where it intersects. All we know is that they're non-zero, so it has to be at least a tiny circle or ellipse around the origin. Whereas the hyperboloid of 2 sheets does not have to have that distinction. And in fact, it doesn't. That's what makes it that way. Couple things to note here, and this is something that I meant to highlight with each of these, and I haven't. Okay, so I want you to kind of make a little asterisk here. I've given you one version of each of these surfaces, right? But I said earlier that the order in which these terms appear depends on what axis it's lying on, the way that it's oriented, right? So I just gave you this as x squared plus y squared minus z squared. But what if you had, x squared minus y squared plus z squared? Well, then it's just going to shift in the same way that you see it oriented here, right? This is in the x, y, z. So the hyperbolas are opening up to the z-axis, or rather you could think that the ellipses are running along the z-axis. So if I had it a different way, where it was the y squared was negative, then they'd be along the y-axis, and this thing would be lying in this direction. All right, so this would be like x squared minus y squared plus z squared equals 1, something like that. So depending on where this negative sign occurs, if it still has 2 are positive, 1 is negative, and it's equal to 1, that's just going to change the way it's oriented, right? So it's still the same thing, but just lying in a different position. Does that make sense, or did I go too fast with that? Okay. And the same is for all of them. So just if there's something, the ellipsoid's the only one where they're all positive and it all equals 1, so the order doesn't really matter. It's all commutative. But with all the others, there's pretty much something that can be changed, and that means it'll change where it's lying on the set of axes. Okay. So I'll just write in here where negative falls dictates orientation. Okay. Awesome. It says a hyperboloid of 1 sheet. So a hyperboloid of 2 sheets then is going to have this form. Z squared over c squared minus x squared over a squared minus y squared over b squared. So you see the x and y are both negative here. And again, think about y equals 0, x equals 0, z equals 0. What are these things going to look like? Well, to be super fast about it, right? Cut out x. I've got a hyperbola in the zy plane. Z squared minus y squared equals 1. In the y equals 0, I've got a hyperbola z squared minus x squared equals 1. And when z equals 0, I've got negative x squared minus y squared equals 1, which is what? Well, they're really ellipses, right? Again, it's just negated. But what we don't have is an intersection point in the middle. Did I have a... No, I thought I had an extra note there. That's okay. So what this ends up looking like something like this. We've got two hyperbolas intersecting with these elliptical top and bottom, but this is why it has two sheets, is because there's this break. Okay, so again, to just note the signs on things and where those signs are. So two of the terms are negative, one is positive, so this hyperboloid is lying on the z-axis, right? Because that's the positive one. All right, and in the very last one, and then you'll have some fun problems to practice these with. Again, it can't be replaced to talk about these things versus just going in and playing with them, because that's really when you're going to drive the familiarity with them. Because, just seeing and maybe seeing just once, okay, the x is negative, the y is negative, you don't really have it yet. So make sure to jump on the practice problems as soon as you can. But the last one's a really interesting shape, and the reason that it's interesting is it's a great example of why things don't just port directly from Calc in 2D to Calc in 3D. Okay, so if we look at this thing, if I had y squared over b squared minus x squared over a squared equals z over c, and we'll say that c is positive for the moment. Let's think about the traces here. These little snapshots of the curve, or the surface, not the curve. Snapshots of the surface. Well, when x is 0, z is y squared. It's a parabola, right? Upward facing. Z over c. Well, I'll just even solve it. Z is what? C. Where'd my pencil go? There we go. C over b squared y squared. That's a parabola, upward facing. If I look at y equals 0, then that tells me that I've got z equals negative c over a squared x squared, right? I've got a downward facing parabola. So x equals 0. So this is the zy plane, not zy, yz plane. So in that front wall, side wall, downward facing parabolas. And when z equals 0 in the xz plane, we've got what? Y squared minus x squared equals 0. And so we get the what do we get right there? Nothing helpful, because it passes through the origin. So we'd rather look at like z equals z naught or z equals k. So when z equals k, we've got y squared minus x squared equals k, which is really a hyperbola, right? Something like this. And so, what does this thing really look like? It's kind of tough to draw. I'm going to try it right now, but then I'll use a computer to actually show you what's happening. Okay, so here what we have is in the xz plane, we said we had downward facing parabolas. So over here we've got one trace here, and the same happens actually over here. And then in the yz plane, so let me just label these so we're super clear. In the yz plane, we have upward facing parabolas. So it comes down something like this. I'm actually going to redraw that to be like that. And then in the, and I'll put one more down here. When z equals 0, this is still a downward facing parabola like this. And then we've got hyperbolic cross sections when z equals k, doing something like this. Okay, and while I've done a real bang-up job of drawing this thing, you say, Mally, you're such an incredible artist. Where did you go to art school? We're so impressed. Thank you. Self-taught, actually. But what this thing should look like is a saddle. Okay, so I don't know if you can kind of get the sense of it being a saddle here. Right, kind of falling off on the other side. So what this is called in the center here, this is called the saddle point. Talk about that in a second. But this whole shape is called the hyperbolic paraboloid. Again, we don't try to name things super creatively in math. We call them what they are. Hyperbolic paraboloid, because it has, what, traces that are hyperbolas and parabolas. They're upward facing in this direction, right? They're downward facing in the other, and then we have hyperbolas along the side. So you can kind of think about this saddle being formed, and I'll show you guys a better picture of this. There we go. Okay, so you see a little bit better what's happening here, and you can see the cross sections, the downward facing parabolas in the xz planes, right, and the traces of y equals k. When x equals k, we have upward facing parabolas. And when z equals k, if you look top down, you can see these traces of the hyperbolas, right? And then at the origin, that point where we didn't get anything, it's crossing through the origin. So at the origin, we have what's called the saddle point. And the reason that this is a really cool shape is that it starts to defy our idea of what does it mean to be a max or a min, right? If you remember back to optimization in Calc 1, we want a point that is, either higher or lower than the other points around it. Well, this point is super interesting because based on what direction you're looking at it from, it's either a max or a min, right? If I look at it from this direction, it's the vertex of these parabolas. Looks like it's the highest point, but if I look at it from this direction, it's really a minimum. And so this is why that notion of a derivative along just one axis, right, or the idea of slope breaks down, because it looks like it's increasing to a max if I'm walking in this direction, but along these paths, it's a minimum. So just kind of a fun visual thing, and just something we also need to look out for, right? Before, when you were looking at optimization problems, you'd use the derivative test to identify those critical points, those interesting points. Now, you might think, what's if you were able to port the idea over. I'm kind of fast forwarding a lot right now, so I hope I don't lose you too much. But what do you think the derivative would be? Big air quotes, because we don't have a 3D version of the derivative yet. But the derivative, if we're just looking at the 2D traces, it'd be 0 at that point, right? Because it's a min or a max. But in 3D, we don't have kind of a name for what's happening right here, and this is what that is. It's a saddle point. So this is something else we got to look out for now that didn't have a 2D equivalent. There was no such thing as something that could both be a max and a min at the same time, right? So depending on what direction you approach it from. So that's one of the many reasons why we're going to be looking at what's called partial derivatives. A derivative in a given direction, because it turns out to matter what direction we're moving in when we're talking about surfaces, right? And then go up to Rn, n-dimensional space, it matters even more. So anywho, that's just a little bit of a preview of the calculus we'll be doing later, why we need to care about these shapes, and why they're kind of interesting and different than what we've played with before. So that was kind of a lot of formula dispensing. It's really the best way I found to kind of work through and get you guys comfortable with this material, to kind of hand these off, show you how to view through traces, because that's a skill that we're going to use throughout the rest of the course, and then to really give you a lot of good practice time to become familiar with them. So, questions for me? Comments? Concerns? Protests? Awesome. Good work. Good questions. Oh, we didn't get back to the other ones. Let's do that quickly, right? Now knowing what you know. You thought we were going to leave. All right. So, knowing what we know, we're pretty comfortable that 6 is graph 3. Which ones didn't have a home yet? Pretty much just 5, right?
We just left 5 with 5.
Oh, so process by elimination. That's kind of lame. All right. So 5 was 5, but let's reason out why. And we have a name for this type of graph, right? Which one is this?
So it's a two-sheeted a hyperboloid of 2 sheets, right? Because it has 2 negative values.
It's got 2 negative terms. That's right. It's a hyperboloid of 2 sheets, or a 2-sheeted hyperboloid. That's right. And how do we know that this is the correct formula for this one? Besides the fact that there are no other 2-sheeted hyperboloids, how do we know that this one is definitely the right one?
Since x is the positive value, we know that the x has to kind of be the axis that it's on. If we think of it being like going through the points of our sheets.
Yes, absolutely. So x is the positive term, and so that's the axis it's lying on. In the kind of canonical description, z is the positive term, and it's up and down right on the z-axis, and that's where the elliptical cross sections are. But now it's flipped on its side, so it's going along the x-axis. So great. So yeah, we found a home for all these. That is great. there's a couple problems like this with the matching that will stretch your understanding a little bit more. It'll get into more of the general shapes, which will be good. But all right, make sure that you're, using the class discussion if you want to, kind of have an analog for raising your hand, and we can all jump in on that too. So we can kind of leverage the fact that even though this is a live class, that we have the online tools. So don't be afraid to post questions, homework problems you're working on that you want to kind of crowdsource, or have me jump in on, and then we all get the benefit of seeing the answer. So I'll just throw that out there as a option for you all. All right. Great work. Have an excellent evening, and we'll see you on Thursday.